So we decided that we should probably do a review video going over the maths that we just covered and kind of get into the weeds with a little bit more detail. So what we had done in the last video is derived very significant mathematical constants of nature just by simply playing with the existence equations. And so a brief review, what we did was we derived the existence equations where we have this continued fraction that has this value. And one of the neat things with the existence equations is that we showed that we're able to take this continued fraction part and set it equal to n star, or this part over here and set it equal to u star. Sorry for my sloppy handwriting. And what that did was gave us a tool where we could show that these series actually converge. And then what we did was we played around with the series a little bit and showed how we could actually get these two equations where we're basically just dealing with this little extra continuum of infinitely smaller and smaller components that get added to create n star or subtracted to create u star. We're able to isolate those little components, and because this actually ends up being a negative number, we need to run a reverse sign through it, and then ultimately what we end up with is n star minus the initial n over the initial u minus u star gives us a ratio for corrections between a and b with these continued fractions. So with these equations, that's how we got the following. So if we took a particular value where we let a equal 100 and b equal 20 for a over b, where we derive the continued fraction, when we take the correction component and we add it to n star minus I squared, we end up getting a very close approximation to the fine structure constant. And then when we subtract from it this value, which turns out to be 137 divided by 2, we get a value for the fine structure, the inverse value of the fine structure constant, that just so happens to be off by a correction amount associated with the CKM matrix. What we find is that our version of the fine structure constant versus the experimental version of the fine structure constant is accurate all the way out to 1, 2, 3, 4, 5, 6, 7, 8 decimal places, which is very significant because if we take these two values, the fine structure constant based on the existence equations, and subtract from it the experimental value and divide that by b, we get the ratio of baryons to photons in the visible universe. But what's even more interesting is if we take those numbers and we just go ahead and inverse this, so we have the inverse of alpha from the existence equations minus alpha from experiment, and multiply that by the ratio of baryons to photons, and then multiply that by a, we return back to the number 5, which is the ratio of a to b, but it's also the ratio of visible matter in the known universe. So just from playing with these numbers with the existence equations, we get the ratio of the visible known matter, we get the ratio of the baryons to photons, we get a correction for the CKM matrix, we get a fine structure constant, and we get the number of elements that are possible in the periodic table, assuming the fine structure constant value. So, what we wanted to do today was kind of go over this in a little bit more subtle detail. So Matt, what do you got for me?
Sure. Well, number one would be just what you referenced, the theoretical or hypothetical limit to the number of elements in the periodic chart.
Okay, so what's interesting is that when I derive this equation, I just put the number 137 in here because just at a quick glance, if I subtracted 137 from the 137 number I had and divided it by 2, but then subtracted that again from that number, I got a number very close to the fine structure constant, which interestingly is off by an amount that's similar to that which we find with the CKM matrix correction. Now what's interesting about this particular correction is it has to do with what's called superallowed beta decay. Now, this is where the correction comes in, and what I find interesting about that is that the idea of superallowed beta decay is actually extremely consistent with the model that we have for how the existence equations apply to the hydrogen atom. And that's something we could go right into.
One of the first things we wanted to talk about was fine structure constant and the spectral lines.
Okay, so what fine structure actually has to do with is that when we actually look at spectral lines from elements, there's black missing areas, missing bandwidth, and what that represents is the electron shell or the orbital of the energy level of that electron in that element. But when they closely examine the spectral lines, what they saw is that they split into more than one, right? So
Right.
This is ultimately where the fine structure constant gets applied. But what's really interesting is that when we apply the existence equations to atomic structures, one of the big assumptions that we come away with is that the hydrogen atom should actually have both electrons and positrons orbiting it. So what I would argue, and positrons going reverse in time. You know, the big question is, where's all the missing antimatter? Well, I would argue the missing antimatter is here, that all matter is composed of both particles and antiparticles. However, there's a neat little thing, and something I can demonstrate with the existence equations, where though these particles have the same quantum numbers, because the positron is going backwards in time and the electron is going forward in time, their orientation with one another is slightly staggered, and that's what prevents them in an orbital from annihilating. In essence, what you have is the forward in time moving electron and the reverse time moving positron are trying to catch up with one another, but because there's a slight offset in time where one is in relation to the other, they never can quite get to where the other is by the time the previous one gets there, and vice versa. So they never collide. And so essentially that's what the electron shell is the positron electron energy potential in a time loop.
Sure, as I like to call it, the cat chasing its tail.
Yeah, there you go.
Great. You want to move into the baryon-photon ratio from there?
So that takes us into the baryon-photon ratio, right? And that's basically what we just discussed. So if particles and antiparticles had perfect symmetry, then the argument is there wouldn't be anything in existence, because all of the particles and all of the antiparticles would have zeroed each other out. So the question is, well, how is anything here? One, and two, why does everything we look at appear to have only particles? Now, this gets into some very esoteric aspects of how existence is applied to physics, but I have some old printouts here from a long time ago. In fact, these were printed out back in 2002, and I'm going to go through the stages of how cross symmetry works, applying the existence equations to physics, to explain how we came to the conclusion that matter is composed of both particles and antiparticles.
Sure.
So on here, if we look, we can see we have all of the quark flavors and their charges laid out in a box, if you will. And if you notice, there's an interesting relationship between the down quark and the up quark, or the strange quark and the charge, or the bottom and the top. And that is, there's a 2-to-1 relationship between up and down, charge and strain, or top and bottom. Again, I just wanted to note that. So, here we go ahead and we draw out the quark in cross-symmetrical form. So let me go ahead and draw this. So the idea that we have here is that we basically have something coming out of the vacuum, something going back into the vacuum. So these two states zero out. Or the reverse, something anti coming out and something anti going back in. So these have a cross-symmetrical relationship. If I reverse this one, it's equivalent to that, or if I reverse this one, it's equivalent to that.
Sure.
Right?
Yep.
So the idea is we go ahead and draw out these quark cross-symmetrical relationships, the up with itself, down with itself, charm, strange, top, bottom, etc. So the idea is that since we have a spin or charge relationship between where the up has the same charge as two downs, or two downs has the same as up, we're going to go ahead and do a swap with these. So idea, again, going back to this, that we basically have like a quantum soup of potential orientations of all the different potential virtual particles, if you will, and there's a statistical probability to end up with this relationship popping out of the vacuum. So then, here's the quark soup again. So here I'm showing the down configuration plus a down configuration will give me just twice the configuration. And then if I do a cross-symmetrical swap between the up quarks and the down quarks, what I can get is the following. And basically by rotating one in relation to the other by 90 degrees, which is interesting, I end up with a neutron, an antineutron, and then two sets of unstable configurations, right? So we'll go ahead and sort of draw this nicely. So here we can see this sort of almost in like an atomic structure, how we're going from those symmetrical relationships into neutron, antineutron symmetry, right? And then what happens with those extra components is those become the three different potential pi meson configurations that then decay. So in essence, what we've just done is we took one up quark configuration with two down quark configurations, rotated them 90 degrees out of phase with one another, and then brought them together so that what we end up with is a neutron symmetry, anti-neutron symmetry, meaning neutron going in, neutron going out, anti-neutron going in, anti-neutron going out. And then we're left with three pi meson configurations, which then decay. So because the pi mesons decayed, and because there's nothing for the neutron, anti-neutron, in and out configurations to couple with to return back to the vacuum state, they're stuck in a matter configuration. So basically, what stabilizes matter is it's a process that would have returned back to the vacuum state, but because there's a missing component, it's stuck in a time loop.
Yep.
So here we can see the time loop configurations to show how we have a clockwise forward time and a reverse counterclockwise symmetry, right? And so what we get is proton, neutron, antiproton, antineutron symmetry that we generate with this. And so what you have is, you have super allowed beta decay where the neutron is disintegrating, reconfigurating, right? Without the loss of energy, but the superposition of the neutron in disintegrated form, going in the vacuum or out of the vacuum, being stuck in a time loop, that is your hydrogen 2 atom. So in this model, H2 is actually the base element, not H1. And from H2, we have electron and positron orbital, where the electron is forward moving in time, the positron is reverse moving in time, through a forward beta decay, reverse anti-beta decay superposition. Does that make so? Basically, H2 is a superposition of beta decay and reverse anti-beta decay, and the 4 configurations of those locked in a time loop. Does that make sense?
Yeah, absolutely.
So that's why we have a double spectral line. It's to account for both the forward and reverse time aspect of the time loop that stabilizes the atomic structure. And I think this illustration does really well of demonstrating super allowed beta decay. But what's interesting about this super allowed beta decay is it's actually half Majorana, half Fermi. If you have the neutrino as its own antiparticle, so that the neutrino potential is locked inside this decay mode, then it's a Majorana particle. But if it's able to emit through a weak interaction, then it's a Fermi particle. So really and truly, this is a balance between Fermi and Majorana statistics. And so what I'll do then is do this image. So here you can see sort of the time loop, forward time, reverse time, forward time, reverse time, and the super allowed beta decay that's forward, reverse, forward, reverse, forward, reverse, but all in a linear fashion, right? And then what's really neat is we can take all those 4 different potentials and put them in the 4 square. Let's let the top be the stable configurations,
Sure.
the bottom being the unstable configurations. So this would be matter composed of particles and antiparticles, and this would be matter, antimatter composed of particles and antiparticles, but the matter are the stable configurations of particle to antiparticle, and the antimatter are the unstable configurations of particle to antiparticle, and that's where we get that ratio of 6 times 10 to the minus 10th is the ratio within here that makes this stable and that unstable. So with the Wu experiment, we saw that there were more left-handed moving there were measured left-handed electrons more than right-handed electrons. And so my argument is what we're actually seeing is that the forward-moving electrons, right, are the bound, and the reverse anti-electrons are what's radiating away. So what it is the left-handed matter is associated with unstable configurations, and the right-handed matter is associated with stable configurations, and that's why we don't see any right-handed particles, specifically right-handed neutrinos, because that potential is locked in the super allowed beta decay, etc. So that's basically that.
Great.
In a nutshell.
Beautiful. Very elegant. Now, does this lead us into the 50-50 equation?
Let's do the 50-50
Sure.
since you brought that up.
Sure.
And then I'll bring up.
Lead us into the CKM after that.
Yeah.
Okay.
Now, going back to the existence equations, there's actually something really peculiar about them. And that is, so let's go A over B, right, plus A over B plus A over B, right? When we simplify this, what we end up with is that A over B minus 1 equals N star, and that B over A plus 1 equals U star. And you guys can go back to look at previous videos where I demonstrate this. What's peculiar is this, and then what we end up with is this equation where for all A and B, N star minus I over I minus U star is always the case. And before I forget, I is basically U star times N star. And it serves as sort of it acts in the same way as 1 does if U and N were reciprocals. Hence the identity constant. So what's a trick though, is this still works. Move it right there. That still works if A and B are identical. So this is really strange. So I'll go ahead and demonstrate that.
Sure.
All right, so if we have A over B, and let's let that equal 20 over 20, right? So in this case, what we would have is that N star would equal 20 over 19. You can go ahead and calculate that out for me. And U star would equal 20 over 21. I'll do the 20 over 21.
Sure.
So 20 divided by 21 gives us 0.9524. Okay, and then what do you got for 20 over 19?
That equals 1.05263. We can cut off the 4 digits.
We'll cut off the 3.
Sure.
Okay, so now, since you've got yours out, let's go ahead and solve for I. So what's I equal? So I is 1.0024. Okay, so now if we subtract 1.0024 from 1.0526, what's that give us?
That's 0.0502.
0.0502. Okay, and then what's 1.0024 minus 0.9524?
0.05.
02.
O2, yeah.
Okay, so even when A and B are the same, the existence equations still work. So in the case for the way we could interpret this is even though an electron and a positron, right, have the same quantum numbers, the electron is further in time or further along some trajectory, 0.0502, and the positron is behind 0.0502. So this has significant applications in applying to, if we assume that there's a positron and electron in the orbital in a superposition, then this actually helps us define that.
Sure. So I guess from there then, Gavin, we can go into the CKM error correction.
Okay, so what's a trip is that when I saw the CKM triangle, what I realized is I could apply the existence equations to the CKM triangle just because I can. It's, that all the existence equations always derives a right angle triangle. The secant metric requires having a right angle triangle to maintain what's called unitarity between asymmetries, right? So that you maintain unitarity for conservation of symmetry, right? And so what was interesting is that I could apply the CKM, the unitary triangle, in multiple planes, because when I apply the existence equations to physics, we get 3 time dimensions. So I can have the CKM metric apply to one plane or another. Because mass is temporal in nature, what this predicted is that we would have some kind of additional symmetry breaking that we would observe as mass violation. So what's interesting about that is that recently Fermilab measured the W boson to have a slightly different mass than what was predicted or what's been observed at other labs using different techniques. And I would argue that's the first observation of M violation.
Great.
So yeah. Yes, and then the final part, I guess, is how all this applies to visible matter. And so what's interesting is that the long and short of it is all of these unitless numbers that we were able to derive with this equation all have an intimate relationship with one another in physics. So visible matter, since it's visible, we're going to see spectral lines, right? And it's the spectral lines that we're going to need to have defined structure constraints in order to understand it. But the visible matter is also going to be composed of particles and antiparticles based on our reasoning. And those are going to have to follow symmetries that aren't accounted for, that the CKM error correction seems to account for. And it all pertains to the number of elements that we can have as visible matter. So it's just really wild, but all of the parameters that were used in these expressions are all self-contained, and we're not actually bringing any random numbers into this to make it work, where then we have to explain that number away, right? Like the whole purpose of this is, why 137, why 1 over 137, right? Well, we've demonstrated that without bringing in any weird special numbers. And one thing that I think is interesting to note is that when we actually look at the numbers we started with, which is A over B, where A is 100 and B is 20, the n star value is 100 over 19. And Matt, how many parameters are there to the standard model?
Depending on who you talk to, it's either 19 or 20.
So it's either whether we're using the corrections or not.
Right. Pretty convenient.
Right? And so that's basically it.
Very cool. Well, Gavin, that was great. I love the way everything became very integrated and one concept leads back to another. And I think these equations and concepts are truly something to be looked at even further. And it's amazing to me how they appear in so many different mysteries of physics.
Right.
So thanks for explaining that. Really great.
And one thing I'll leave you with, because we got to lead into the next video. In the next video, what we'll get into is we'll get into the nuts and bolts of the fact that the existence equations suggest that if they're real, there's an error that needs to be corrected in the Lorentz transformation. So we should see things arriving ahead of schedule based on relativity, and we have that. Gravitational waves have been measured to travel faster than the light coming from the same source. But we don't have just one data point, we have two. So not only can we take those two data points to actually get in the weeds on some math, but what this goes towards is resolving the cosmological crisis and whether or not the Big Bang actually happened. So I
Great.
think that's a good setup for our next video.
To be continued.